Okay, in this example, we're looking at a potential energy function shown here. It's a function of r, okay? And we're going then to be given the constants, alpha and beta, and we're asked a couple of things about this potential energy function. And they relate to force, okay? And a type of equilibrium. So let's define the formula we're going to use here. Okay, so for part A, we're going to have the relationship that force is the negative of the derivative of potential energy with respect to, well, the distance that the potential energy is a function of, in this case r. Okay, all right, so it's the negative of the derivative, so we can find that function. Okay, so let's get back in frame there. All right, so negative d dr, and then our original function, alpha, r to the 8, okay, minus beta, and then r to the 3rd. Okay, so we'll go ahead and do our rules of differentiation on that. Okay, so what that's going to look like is a leading negative, and we're going to have 3 alpha over r to the 9th over here. Okay, and oh, actually here, let's take care of our negatives because this gets a negative of its own. All right, so we'll distribute that. There we go. And then here, this will become 4 beta and then r to the 4th. All right, so there is our potential energy. Sorry, there is our force function now. Right, so we had our potential energy as a function of r, and now we have our force as potential of r. So if we're looking for an equilibrium is going to correspond to a force of 0. Right, because we're looking for a slope of 0, because the force represents the instantaneous slope of the potential energy function. So we need that intercept of the force function. Okay? So to find the, so the equilibrium distance, equilibrium separation, so define r equals, and you'll think about, so we'll call this r equals r equilibrium. We set the force function as a function of r equal to 0 and solve for r. Okay, and let's do that. And I want to show you a graph that will help us make sense of it. Okay. Okay, so I've included the graph here that shows the original potential energy function. All right, so that's indicated right here. All right, and okay, so there's our potential energy function, and we see that it has a particular shape where it bottoms out, and that's happening right here. Okay, and then this upper graph shows that part zoomed in. Okay, for those same values. This right here would be the r-axis. Okay. All right, so r, and then this axis right here is potential energy. Okay, and so that's what we're looking for. That is going to be our point where the slope, right, the slope at that point has a tangent line that's 0, so that's going to be our equilibrium. Okay, and I mean it looks like an equilibrium on a potential energy graph. So, but that's the relationship between force as the second derivative of the potential energy. Okay, all right. So let's go ahead and solve for that value back in our expression here. Okay, so we want to solve for r. So the way we're going to have to solve for r in this problem is to solve it with a equation solver. All right, that's going to be the form to take. All right, and here, since I don't have an equation solver installed on this emulator, the TI-84, on the screen, instead I'm using Wolfram Alpha here to solve the equation. Okay, so just went to wolframalpha.com. All right, and we're finding the zeros of this expression. All right. All right, and these are expressed not in a decimal form. So let's see what we want to do about that. Okay, so I realize here that I just wrote down my numbers wrong from when I did the derivative. Right, I mean, if you may notice the numbers before, it made no sense. But of course, we have an 8 right here on the derivative of 9, and then a 3. And then the signs changed as well because we were taking, because of the product rule, because we would have had a -8 pulled in front, like right there, and a -3 pulled in front. And we can distribute the negative as well, right? Actually, we can take care of that in this step here and make this one positive and make this one negative. Okay, so that's the function that I plugged in to be solved on Wolfram Alpha. Okay, and so this is also something that I do frequently on a TI-89, and I know you can install software here. Okay, so all I've done that's different from my previous time that I showed Wolfram was I changed the mode from exact form, which is what is the default. So I clicked a link here, so I'll go back to exact form, and I just changed it to approximate forms. And that's going to give me the type of solution that I would see come out of a TI-89, for example. With the TI-89 default, just showing the real solution. Here, Wolfram shows the 4 imaginary solutions as well, right? Complex numbers. Okay, but the one we care about in physics, the one that has physical meaning, is the real solution. And that gives us 0.018. So we'll go back and notice, all right, that is consistent with the graph we saw before, because this value here is about 0.018, right about here. All right, so let's go ahead and write in that solution. All right, so solve for r, and that gives that the one solution to setting the force function to 0 is r equals 0.018. Okay, we'll include a third significant figure, with the third significant figure being 4. All right, and this is in meters because all of our measurements were in meters. Okay, and so that's the answer to part A. In part B, it simply asks, is this value a stable or unstable equilibrium? Well, we can actually look at the graph that I included here, right, which is also from wolframalpha.com, and it clearly shows that it's a stable equilibrium. So we can say that the graph of u as a function of r shows that equilibrium is stable. Okay, and of course you could have found this minimum through graphical methods rather than through an algebraic solution. You could have, for example, graphed this on the TI-83 and then just found the minimum. All right, and we can also show that the second derivative test at that value is less than 0. All right, so let's do that. Okay, so here I've just shown the derivative of the force function as a function of r. Okay, and which is the second derivative of the potential energy function as a function of r. All right, so we see the values here, and we've got our values for alpha and beta up above. Okay, so if we plug in the r that we now know is an equilibrium, which rounding here is 0.0184, and I stuck with that rounding, but we will at least, especially because we're just looking for the sign here. So I've entered it here into the calculator on the emulator, and we're going to get a value that is negative. Okay. Okay, but of course that doesn't make any sense for the second derivative to be less than 0, because clearly we have a local minimum, which means we need positive curvature. But here's the issue. What I wrote here was the second was the derivative with respect to force, but we actually want the second derivative with respect to potential energy, because if I had actually taken the derivative of force with respect to r, I would not get the second derivative of potential energy with respect to r, because of that extra negative, right? The extra negative right here. And we never cared so much about the direction of the force, which is the reason for the negative that occurs here. Rather, we were only interested in where the force was 0, which is where we set it equal to 0 in order to find an extrema. Okay, so the point is that my signs on this function are incorrect. We should have a negative here and a positive here. Okay, All right, and so then when we insert that into the equation, all right, so if we put a negative, all right, okay, and we want to make our second term positive, okay, sure enough. All right, so I'll just change that one. Okay, and then we find the value at our equilibrium location of 0.0184 meters, or 1.84 centimeters. And when we do that, indeed we find that it's greater than 0, which tells us that it's stable. Okay, so either you can do it graphically or you can do it with the second derivative test. All right, thank you.